So before I get back into this, just one thing I thought that I wanted to say. So the module that I posted over the weekend, if you've looked at it, you may have noticed. If you haven't looked at it, I'm telling you that it does involve some writing some Disco code, but unlike previous modules, I didn't give you like a Disco file to start with to fill in stuff. So you just have to make your own. In theory, you should have enough experience, and you can look at examples we've done that you can just make your own file from scratch. But I thought it was a good opportunity to say, right? I know that sometimes it can be frustrating if you're like, I think this code should work, and it's giving me this weird error, and I have no idea what it means, right? In that scenario, please, just send me a quick message on Teams and be like, hey, here's this file. It's giving me this error. I don't know why. Can you help? And probably I can look at it and be like, oh, it's because of this, right? So please feel free to do that. Don't feel like, oh, I don't want to bother him, or like, I need to figure it out myself. I mean, sure, if you can figure it out yourself, that's great, but I don't want you to be stuck on like Disco syntax. I want you to be stuck. If you're stuck, I want you to be stuck on math concepts and figuring it out. But the Disco syntax is not super important. So, yeah, that's all I'll say. Alrighty, so we were talking last time about induction, recursion. Right, so we defined a bunch of recursive functions in Disco. So we first defined some recursive functions in natural numbers, and we proved things about them by induction. Thought about how induction, what that had to do with defining things recursively. And then we saw actually a type which is defined using recursion. Right, so we saw this endlist type, which represents a list of natural numbers. And this as an end list, is either, that's the plus, either a unit value or it's a pair of a natural number and an end list. And so that looks like, for example, this would be a value of that type. So what I want to do today, I want to continue this. Probably we'll start by writing a few more example functions that work on end lists. And then and later we'll define another kind of recursive type of some kind of trees. And then I want to think about how do we prove things about some property that all end lists would have. And we're going to use a variant of induction, but we can't use the induction that we've seen before because it only works for natural numbers. So that's kind of where we're going. And we'll see that actually the induction that we've learned so far in natural numbers is really just a special case of a more general kind of induction that works on kind of any recursively defined things. Okay, so let's start by writing a few more example functions on end lists. So for example, I don't know, let's find the sum of the values in an end list. We'll write one to find the length of an end list. And let's write one to concatenate two end lists into a single list. So let's start with list sum. Okay, and so as usual, say, well, I'm given an input which is an end list. I want to pattern match on that to see what it looks like, and use that to decide what to do. So, right, it's either a left unit. In that case, the sum should be 0. I don't have anything to add up. That's the empty list. Or it could be right a natural number, which we'll call n, list L. Right, and remember, just as a reminder, right, we have this plus thing that says if you have two types, you know, this type plus this type means we're going to either have things that look like left with a value of this type, or right with a value of this type on the right. So here we have either left with a unit or right with a pair. And the idea is what I should put here to add up this list. Sure.
N plus the sum
Of L, yeah, that's right. And again, like our thinking is, well, n list, right, contains this. In this case, we have a recursive n list. So probably, I'm going to call this function recursively on this L, right? So our thought process could be something like, well, this L is an n list, and so I'm probably going to call this function recursively. So I want to do something like, I'm probably going to do this. Right? Maybe I don't know what to do with it yet, but probably it's going to involve calling list sum recursively on L. And probably I'm going to use n somehow, because otherwise, you know, why do I even have n? So then the question just becomes, well, how do I combine these? If list sum gives me the sum of the rest of the list, and I have this n, what's the sum of the whole thing? Well, clearly, if I know the sum of the rest, and I have this one thing, I just add them, and that gives me the sum of everything. So that could be my thought process. So let me just write this down, actually. So thought process to write a function on a recursively defined type. So we're going to you know, write a definition for each case. You know, what pattern match, or I'll just say, actually let's say this one. Pattern match on the input and write a definition for each case. In a recursive case, call the function recursively on the recursive, well, I'll just say call the function recursively. And then we're going to assume it will give the right answer. And I'll talk about that more in just a second. But assuming that does give the right answer, so in this case, like I say, all right, I have this L, which is recursive, I'm going to call list sum on that, and I'm just going to assume that'll give me the right sum of that list. Right? Then all our job is figure out how to combine that correct answer, correct recursive answer, with any other information to yield the overall answer. And let me, and we'll do an example of this again. We write some more things down here. But let me say something a little bit more about this. Assume it will give you the right answer. In my experience, students sometimes find this a little weird because you're in the middle of writing list sum. You haven't finished writing it yet, right? So when we're in this, we're just like, all right, I haven't finished implementing list sum. So list sum doesn't really do anything yet because I haven't even finished writing it. And you're telling me to call list sum and then assume it's going to work. But how can I assume it's going to work? I haven't finished writing it yet. Okay, but this is the way to write a recursive function, and really this has to do with induction. If we're proving that the function works by induction, what would we do? We would say, well, suppose that it works for L, right? I haven't even told you what induction means on lists, but you can kind of see how this is going to go. We'll say, suppose it works for L, then I need to show that it's also going to work, for this. And so that, suppose it's going to work, right? We can actually use that same approach when we're writing it. We say, all right, well, if this did in fact work on do that, then it's actually going to work, because every time it makes a recursive call, it's going to do the right thing with the next recursive call, and so on, down to the base case. And if the base case is correct, then the whole thing's going to work. So we'll put this one. All right, well, let's try that approach here. So list length takes an n list, and it's going to give a natural number. So first step is we're going to pattern match on the input. So we say, all right, well, the input could either be a left with a unit, and I'm actually just going to put dot dot dot. You know, or it could be a right with some natural number and a recursive n list. So now I have to define what I should do in each case. So first I have to say what's the length of the empty list. That's easy, it's 0. Usually the base case is going to be pretty easy. And then in this case I say, all right, it's probably going to involve calling list length L. And then I say, all right, let's assume this is going to correctly give me the length of L. If that's the right answer, that's the length of L, then what is the length of, you know, right n comma L? Which just means I have, you know, this first element n followed by the rest of the list n. So what do y'all think? What would be the length of the whole of the entire list if I already know the length of L?
Would be 1 plus that?
Right, just 1 plus that, right? Because I just have this one thing here, and then everything else is in that list L. So if I know the length of that, I just say, all right, it's 1 plus that. Done. I guess we should probably try these out, right? Do I have? Oh, I have my example list. So I can say list sum of example list 19. Does that look right? 7 to 10? 19. That's right. And I can say the list length of the example list should be 3. 3. Cool. Let's do one more here. This one is a little bit more interesting. List. Okay. No, sorry, I should say. So this function takes a pair of n lists and returns a single n list. So for example, and maybe we should have done this for the other ones, just write down some examples first so we know what we mean. So for example, list concat of, you know, 1, 2, sorry, should be like example list, right, 7, so example list is the list, like 7 to 10. And then if I concatenate it with this list that just contains a 4, I should get 7, 2, 10, 4, just like glues them together. So this should be equal to, let's get it right. Okay. That's just, I mean, we can put more examples, but that's the idea. So, well, how do we do our pattern here? Oops. So one thing you might do is say, well, my input is a pair of n lists, And like each of these end lists, like, this one could be empty, maybe they could be both empty, or this one could be empty and this one could be, not empty. I guess I have like 4 different possibilities for, you can do that and you can write it and it'll work. It turns out, just to save some time, right, it's not necessary. We actually don't need to like pattern match on this one. We really just need to, it really just matters what this first one is. If I have left unit, and this one I'll just call y. Alright, so what do you think? In the case that I have an empty list, and I want to glue that together with the list y, what should be the result? Just y? That makes sense, right? If I do the empty list and I concatenate with something, like I haven't really done anything. There's nothing to concatenate, so that's just y. Okay, makes sense. And then here, it's like, okay, I have this, in this case I have a pair of a natural number and some recursive end list. So probably I'm going to call list concat on L. But I need some other thing here. I guess I might as well just give it y. So here I'm trying to say, all right, I have the first list is a single thing followed by a list, and then I have another list, and I'm trying to glue this together. If I already know what I get when I glue just this part, L, to y, right, what should I do to get the overall answer? This would be kind of like, so using a different notation, I'm going to make it easier to see what's going on. If I have a list, 2, 4, 5, and I'm trying to glue it, I'll just say plus. This should get, I should eventually get 2, 4, 5, 5, 8, right? That should be the answer. But in this case, it's like I've taken this first list apart into, I've got a 2, and then I've got the list 4, 5 after that. And I'm saying that I know what happens when I do 4, 5 glued to 5, 8. I get 4, 5, 5, 8. And the question is, what do I have to do to that to get the answer that I want, which is actually 2, 4, 5, 5, 8. Right, that's right. So I want to, take that one element and stick it on the front. And the way that I stick something on the front of the list, is I use that right, whatever, comma. So I want to say, right, and okay, our test worked. So we could also say like list concat, example list, 7, 2, 10, 7, 2, 10. Yep. Okay. property that we want to prove about this. I realize that the property that I have in mind, I think it's going to have too many annoying details, and I'd rather do something a little, I can think of something a little simpler on the fly. Okay, I go. So, let's say we wanted to prove, so just going back here and thinking about list max and list sum. So I claim that the max of a list will always be less than or equal to the sum of a list. Do you guys buy that intuitively? So the max value in a list is going to be less than or equal to the sum. Because they would be equal if the list had only a single thing in it. Right? Or if it had a bunch of zeros, I guess. Then they might be equal. But in general, like the max has to be in there somewhere, and there might be some other stuff, so it would make the sum bigger than the max. So, the idea is, what if we want to prove some property of all lists? So, for example, list max of L is less than or equal to list sum of L. Sadly, so this looks like, I mean, I wrote it in disco notation. It looks like this is something that you could test in disco. Sadly, right now we cannot. The reason is that in order to be able to handle, basically disco right now can't handle for alls on like types that we defined ourselves. There's no theoretical reason that it can't. It's just kind of complicated. So, and I haven't done it. So sadly we can't, like, because it would be great if we could actually paste this in and say test this out, and it could say, oh, I tried a bunch of examples, seems okay, or it says no, here's a counterexample. Right now we can't do that. So perhaps in the future. But in any case, I mean, we could try some examples, on our own. We could think about it, decide whether we believe this or not. But if we wanted to formally prove it, how would we do this? So here's the key idea. This definition of n-list this is really saying, right, this is the definition of n-list, so that means this is the only way, these are the only ways you can make n-lists, right? And we've kind of implicitly used this fact when we're writing functions on an n-list. If I give you an n-list, then because it's defined this way, you know, it has to either be left unit or it's right with, some natural number in an n-list. There's no other thing it could look like, right? So, for one thing, if we can kind of prove something in both of those cases, right? We want to say, well, I want to prove something about all n-lists. So first of all, I'll prove it about empty n-lists, and then I'll prove it about, n-lists that look like a right of a pair. And that's going to cover all cases. But of course, in this case, we have a recursive n-list. And what we're going to do is we're going to say, all right, well, let's suppose that this n-list has the right property. Then we're going to show that, the whole thing also has that property. And I claim that if we can prove that, then it'll be true for all n lists. Why is that? Well, first of all, we're going to prove it for this base case, like the empty n list. Okay, so the empty n list will have the property. And then we'll say, all right, well, suppose we had, right with a natural number and the empty n list. Right? If we show that if any n list here has a property, then the whole thing has a property, then we can say, all right, well, now we know it's true for any n list that has a single element, because it's true for the empty one, and we proved that if you add a single element on the front, it'll still be true. And then, well, now because we know it's true for things with one element, we can do that again and say we can add one more element on the front, and because it was true for the things with one element, it'll still be true for things with two elements, and so on. And so that will let us conclude that that property is true for every n list. Okay, so I'll write this down and then I'll kind of generalize it a little bit. So to prove something, some property is true for every n list, we're going to prove it is true for the empty n list, that is the left unit. And then we have to prove that if the property holds for some n list L, then it also holds for right of n L. Okay? And the idea is, since every n list is built by starting with left unit and then applying right and L some number of times, this means the property will be true for all n lists. And I hope that you can see the similarity to induction, right, where for natural numbers we said we can prove for 0, and then if we can prove that if it holds for n, it also holds for n plus 1. Right, here we're saying we're not starting with 0, we're starting with, in this case, the empty list. And then we have some step we can do that will build a new list from an old list. And if that always preserves the property, it'll be true for all lists. So let's prove this thing here. So proof by induction. So first of all, if L is left unit, that's the first case. Well, then let's see. Then list max of, I have to show that list max L is less than or equal to list sum L. But if L is left unit, let's see how those are defined. List max of left unit is 0 by definition. There it is right there. And list sum of left unit is also 0, and 0 is less than or equal to 0. Check. So it's true for empty lists. Okay, now we're going to suppose if L is equal to right of n, I can't call this L because I already have something called L, so I'll call it L prime, but L prime. So the first thing we're going to do is we're going to suppose that this property is true for L prime, right? So we're first going to say, suppose that the property is true for L prime, that is, list max of L prime is less than or equal to list sum of L prime. Okay, then, well, we're gonna, let's see, so list max of L equals list max of right of L prime. This is just our definition of L in this case, right? And this is the case where we said we're supposing that L is equal to right of NL prime. So I just substitute. I guess I should really just say like substitute for L. That would be a better way to say that. Okay. Now what? Well, now I can look at the definition of list max and see what list max does when you give it a right something. So here's the definition of list max in this case. So I guess you can't see it at all. It's this one. So this is equal to, by definition of list max, this is equal to, what? Let's see. N max list max L prime. Now what? What can I do now?
Eventually, we're going to get to a point where L prime is less than that, just go back to basics.
Okay, so that's true, but I don't want to keep unfolding L prime, like keep saying, well, L prime could be either empty or left or right. Because I don't know how many times I need to do that, right? Kind of the point of doing a proof by induction is that we handle the base case and we do this induction case, and kind of that kind of does it a bunch of times for us. So we really have to only say like what happens when we kind of do one step. Right? Anyone else? What can I use here? What can I do? I don't have it, like I can't use the definition of list max anymore because I don't know what L prime is, right? It could be empty or it could be left or right. I don't know which. But I do know something about L prime. It's on the screen. Yep.
That list max of L prime is less than or equal to sum.
Right. Right here. Right. This is our induction hypothesis. So all right, we're going to assume that this property is true for L prime, and so I definitely want to get to a place where I can use that fact somehow, because the whole point is, the fact that the property is true for L prime. I want to use that to show that it has to also be true for L. So I claim that we can say this So I guess really there's a few facts about max that we kind of have to convince ourselves of here. Yeah, I mean, like if I have, if I'm looking for the maximum of n and x, if I make x bigger, that could only possibly make the maximum bigger. It can't make the maximum smaller. Maybe the maximum will stay the same if n is actually the biggest thing, and changing x to y doesn't make a difference. But maybe, x will, y is bigger than n, and then the max will become equal to y. But in either case, it's only going to make the max bigger. And then I guess here, also need the fact that taking the maximum of two things is always going to be less than or equal to their sum. Which is true because these are natural numbers. It's not true for like integers, but for natural numbers, x max y is less equal to x plus y. Right, because the maximum of x and y is going to be equal to one or the other of them, and then the sum of them is going to be bigger than that because I'm adding the other way. Well, n plus the sum of L prime that looks like this. Right, so I could say that's actually equal to the list sum of right and L prime. This is by definition of that's equal to list sum of L. But kind of like substitute in reverse. Okay. I don't know, I guess in the end, I don't know if this was like such a great example because there are a bunch of little details here that maybe are not super clear, but the details are not the important point. The important point is how we proved something about all lists using induction. Okay. Let's just, I think for the rest of the time, we are going to define a different recursive data type, and we'll just probably, I think we'll only have time to just practice writing some recursive functions on this other recursive data type. I don't think we'll actually prove things about it, but you could do something very similar to prove things about it. So let's define a type of tree. I'll call it a tree. B for binary. And binary trees are super important in computer science. They're used all the time. But we're just going to make, this is kind of a type of binary tree shape. So it won't actually store any data in it. It'll just be like tree shapes. So type of binary tree shapes. So actually, before I write down the Disco definition, let me write an English definition. So a binary tree is either a leaf or a branch containing a left, I'll say left and right children, which are also binary trees. Okay, so for example, I could draw a leaf as just like a dot. So that a leaf by itself is a binary tree. I could have something that looks more like this. be a branch that has a left and right child, and those left and right children are themselves just leaves, right? Or I could have something that looks like, let's see if I can draw this. Okay, this would be another kind of binary tree, right? So I have a branch here with two children. The right child is a leaf. The left child is another branch that has two children, which are both leaves. Right? So I can keep doing this and make these binary tree shapes. So how would we write this down in Disco? Well, a leaf, so it's an or, it's either something or something, so I'm going to have a plus. If it's a leaf doesn't really have any information in it, so I can again just use unit to represent that. Or it's going to be a branch which has a pair of binary trees, so I can just say B tree. If I wanted to have some data in it, like maybe if every branch actually has a number stored there in addition to having a left and right binary tree, right, I could do something like, maybe I could have n times b tree times b tree, right? It's actually a triple with a natural number and then a left and right. But we'll just leave it as well. So let's define the size of a binary tree. So the size of a binary tree is defined as like this has size 1. I guess there's different ways you could define it. Yeah, for now, let's just say this has size 1, this has size 3, because like this branch counts for 1 and each leaf counts for 1. Here this has size 5, I guess. This is 1, 2, 3, 4, 5. Okay. So we'll count size of the tree. Counts 1 for each leaf and 1 for each branch. Okay. So how should I start? What will be the first step? Look back at our, I'll copy this down here. Right, here's our thought process. So the first step is we need the pattern match on the input. Say, okay, what could a B tree look like? It could either look like left with the unit, or look like a right with two B trees, which I'll call L and R, for left and right. Maybe, I don't know, maybe we should make this a little different, just so it doesn't, this looks very similar to lists. I want to emphasize some of the ways this could be different. We'll do that later. Okay. like, there don't necessarily have to be exactly two cases, right? So maybe we have like, you know, something else. It could be empty or this or that, and then we would have three cases, right? But we'll have two. Okay, so, well, the size of, and if it's a left unit, I think we said the size should be 1. That just corresponds to a single leaf, right? And then here we have the recursive case, because L and R are both B trees. So I say, well, I'm probably going to call size on L, and I'm probably going to call size on R. And then I just have to figure out how to combine those. I assume those are going to give me the right answer, that those will correctly tell me the size of the left and the size of the right. And the question is, if I'm at a branch, you know, like here, and I know the size of the tree on the left, I know the size of the tree on the right, what is the total size of the whole tree? You just add them together. You just add them together? Make sense? So I think, I guess it depends on if we want to count. I think since we said we want to count one for each branch, I don't think this quite does the right thing, because that doesn't, it doesn't account for the branch itself. So if I want to count that, we should just add 1 to that. There's different ways you could define the size. So if we didn't have the 1 plus, basically it's only counting how many leaves it has.